lab did. Next. At this point, we started also looking then at applying external electric and magnetic fields to the cell. And I mentioned, this is a little plastic cell, about 1 inch square, and in this case, we had a gold foil. We have a couple of strong neodymium iron boron magnets. We also, for our electric field, and even though we're working with the Navy, there was no funding to do this. So as a department head, I was providing some funds, but we were working largely on our own time. So we went out to a used electronics store, bought a power supply out of a television set that would produce about 3,500 volts DC, literally taped 2 copper strips to it. There's no current flowing through here, and that's how we generated the electric field. And again, we could either do the put the cathode horizontal or put it vertical, and depending upon what we were trying to do, or to test out various the effects of these fields and how they were applied. Next. When we did that, then here's an E field. Remember, this is what the cell morphology looked like when without either any electrical or magnetic field. In the case of putting an electric field on it, we saw formation of fractals, saw some things, some long wires. We saw, some little craters form, some folded thin foils. Here was a very large crater that was formed. Next. We also saw these craters that looked like they were ejecta, where we had some sort of a nuclear event. Remember the little flashes that we had? When we did the IR camera, in this case, we had enough energy there that it looks like it caused a little volcano underwater, because all this happens under a solution that came out and then re-solidified. And you see we have a lot of these. This is a picture of Roger Stringham, who was doing sonofusion, saw some similar things when he was bombarding a sonofusion against a palladium foil. Later, we began to realize the consistency of these, the size and so on, and so I'll say a little more about that when we get there. In any event, such volcanic eruptions indicate a lot of energy was being released in a very short period of time. Next. Another thing was we looked to see what was happening to the materials. Were we getting any transmutations? And so if we took a scanning electron microscope with EDAX and looked at it, all of a sudden we were seeing lots of aluminum, magnesium. We saw oxygen. Now, we didn't count oxygen because obviously there's oxygen in the D2O, but it should not be on the cathode. The oxygen evolves on the anode. So should we count this or not? If we looked out on the rim, we might see in this case more magnesium and aluminum. Look, remember that we started out with palladium. So the palladium is down pretty low. So in these areas, we had more aluminum and magnesium than palladium. Next. Sometimes we had a blister form like this, and you can see if we looked here, we might see zinc, aluminum, silicon, magnesium, chlorine again. That was in the solution, calcium, and zinc. So anyhow, a lot of materials, and we published this in Nature Wissenschaft in 2005. It took about 7 months of back and forth with the reviewers to convince them that this was not contamination. They kept saying, well, how do you know it's not contamination? We had the pedigree of the chemicals that we used. We had all of that information. We had kept samples of all of that so that we could test it. They came back, well, there's some of this stuff is in the air. How do you know? Did you seal it off? Did you do? And we responded. Finally, the electrochemist sent a note back to them in a response and said, several of these things can't be plated out of an aqueous solution, so we could have put them in the solution to begin with, and they would not have plated out in an aqueous solution. So what do you want to believe? Do you want to believe that we have new chemistry and physics here then that we're plating these out, or do you want to believe that this is something that was transmuted and created during the cell? And at that point, they agreed to publication. In the case of a magnetic field, a little bit different structure here, sometimes a little bit more compressed, a little flatter. We still see these ejectocytes, and the main difference here is all of a sudden we're seeing a lot more iron than we had seen before, and even some nickel, chromium. The main difference here was the observation that we were observing and are obtaining more iron. Next. Now, we weren't the only ones that were reporting transmutations, and this list was compiled by George Miley at the University of Illinois. Japan, Italy, Russia, France, China, USA, Japan, so on, were all reporting similar things. 7 of these reported iron, 8 had copper, calcium, chromium, zinc, on down. And this is what we were seeing: aluminum, magnesium. So the ones that I've underlined here are ones that we had observed. Now, in my mind, the strength of this data is the fact that they were not using the same experimental protocol that we were. In the case of the Japanese, they were using gas loading. They would start with a powder, palladium powder or palladium black, put it in a tube, compress it with gas loading, and see, they would see these kinds of transmutations. Others were using a solid foil, so they weren't using the co-deposition approach. So, the fact that all of us were getting the similar transmutations, I think, adds strength to the argument. There's new physics going on here, new chemistry, whatever you want to call it, but clearly something that was not predicted and is not predicted. And I think it would be hard to argue that no single mistake in an experiment, no single mistake in the form of contamination or so on, could provide results like you see here from multiple labs around the world. Next. Okay, I'm going to spend several slides on high energy particles because when you talk to a physicist, that gets harder for them to hem and haw about and say, well, it's not nuclear. And to do this, we were using CR39, which is really polyolidicglycol, polycarbonate, and what it is most commonly used for is your glasses. The lenses in your glasses are CR39. About 40 to 50 years ago, the physics community realized that if an ionized particle impacts this, it will leave a little track down through the lattice of the CR39, and then if you etch it in a mild acid solution, the track, it will preferentially etch along where that ionized particle had gone, and so this was inexpensive. It didn't, since it wasn't electronic, you couldn't say, well, it's electronic noise or one of these things, and it provided a permanent record. So we are using CR39, which is a common diagnostic method for the hot fusion and the physics community. Next. Advantages and disadvantages. Again, this came from a paper written by a member of the hot fusion community, and we talked about how the advantages of CR39 and how it works. I've already mentioned several of these advantages. It's a permanent record, it's simple, it's low cost, and disadvantages are it's not real time, and you don't get a direct readout of some of the energies involved. Now, having said that, since the hot physics or hot fusion community has been using this for 50 years, they have done a lot of experiments where they've looked into how much energy does it take to make a track that's this deep as opposed to one that's this deep, and they have linear energy transfer curves, LET curves, that define all of these things. Next. And in fact here, is the Let curve, and this is for in water. So you can see if an alpha particle travels 10 microns